Hello. This podcast is on center of mass. We're going to talk about why it's important to be able to calculate a center of mass. We're going to look at systems of particles, how to calculate other quantities using the center of mass, and we're also going to find the center of mass for extended objects. First, the center of mass is the weighted average of the position and mass of all the particles in an object or system of objects. So we think of an object, say a baseball, as a single object, but it's actually made up of billions and trillions of individual particles that are a system of particles. Mathematically, we can find the center of mass if we take each particle, its position, times its mass, we sum all of them up, and we divide it by all the masses of these particles. And what we're left with is the center of mass of the system is equal to the weighted average, so that's the position times the mass of the particle divided by the total mass of the object or system. This is important because objects behave like a single particle with all of their mass located at the center of mass, something we don't really talk about, but in mechanics all of these rules of kinematics and Newton's laws of motion and the work energy theorem and all of these concepts we're learning about, they apply to a single particle. Now we've been applying them to objects that are made up of billions and billions of particles, and the reason we can do that is at the center of mass of these objects, the laws apply as if the object were a single particle. So let's look at a linear system of particles. As I showed before, this is our equation to find the center of mass. So along one axis, we call it the x-axis, we would just take a weighted average of the particles. And here's an example. We have a 3 kilogram mass and a 2 kilogram mass that make up the system. The 3 kilogram mass is at the 0 meter mark. What we call 0, or the origin, is completely arbitrary. I could have made this the origin, then this would have been -2, and this would have been +3. I chose this particle to be at the origin. The 2 kilogram mass is at 4 meters, position of 4 meters, so we go ahead and do the calculation. Leaves us with the center of mass in this linear system of particles is 1.6 meters, or right here. That kind of makes sense. If the particles were of equal mass, then the center of gravity would be right in the middle. When they're of unequal masses, the center of mass is going to be closer to the heavier particle. Let's talk about two-dimensional planar systems of particles. Here we've got 3 particles, and notice they're not in a line, so it's not a linear system. They do fit on the plane of the XY axis. We have a 2 kilogram particle, a 5 kilogram particle, and a 4 kilogram particle. Notice that I've picked one of the particles as the origin, but you wouldn't have to do that. We already have the equation for finding the center of mass along the x-axis. We need to, in a planar system, also find the center of gravity along the y-axis. And it's the same formula. It's just that we're using the y position times the particle masses divided by the system mass. We take our particles times the x position, and we get that the center of mass along the x-axis is 2.8 meters. We need to do the same thing for the y-axis, and we get 1.4 meters. So the center of mass is at x equals 2.8 meters and y equals 1.4 meters. We can represent the center of mass as a position vector. So in this case, the center of mass of this system of 3 particles would have a displacement vector of 2.8 I plus 1.4 J units of meters. Let's take a look at 3-dimensional systems. For this, we need to find the center of mass along the x-axis, the center of mass along the y-axis, and the center of mass along the z-axis. You can see that the center of mass along the z-axis is calculated the same way as for the x and y axes. And we can represent this 3-dimensional center of mass as a unit vector. Let's look at a real-life example. We're going to look at a water molecule that of course consists of an oxygen atom with 2 hydrogen atoms. The angle between the 2 bonds is 106 degrees. Each bond is 1/10 of a nanometer long, And the question asks here, where is the molecule's center of mass? While we can't see the molecule rotate and move, we know that these molecules are spinning, aka rotating, and we know that they're moving translationally also. How they move and rotate is dependent on and affected by their center of mass. So for somebody studying the motion of water molecules, this is an important thing to know. Well, we have our sketch here of the atoms. So this makes up a 3-particle system. I've placed the oxygen atom at the origin, and I've extended the bond out 1/10 of a nanometer at an angle of 53 degrees above the horizontal axis and 53 degrees below the horizontal axis. The mass of the hydrogen atom is 1, happens to be an atomic mass unit. The mass of the oxygen atom is 16 atomic mass units. We're not so much concerned about the units as we are the relative masses. Next, we have to find the coordinates of the molecules. So the oxygen atom I arbitrarily picked at the origin, 0, 0. The hydrogen atoms, we have to use some trigonometry to find out their x and y coordinates. So for the A molecule, it's 0.06 nanometers, comma, 0.08 nanometers, and for the B hydrogen molecule, it's 0.06 nanometers, comma, negative 0.08 nanometers. So now we can go ahead and use our formula to figure out the center of mass along the x-axis, and it's 0.007 nanometers. For the y-axis, it turns out to be 0 nanometers. And by symmetry, since this is a planar molecule, we know by symmetry the center of mass for Z is 0 because all of the particles would be at Z equals 0, since this is a planar and not 3-dimensional configuration. Looking at the x, y, and z coordinates for the center of mass, we can see that the center of mass lies close to the nucleus of the oxygen atom. Let's look at how we can use center of mass for calculating other quantities for systems of particles. To calculate the velocity at the center of mass of an object, we use a similar formula to finding the position of the center of mass. It's a weighted average of the velocities. Now we may think that all the particles are moving at the same velocity, and when we do something like throw a football or a baseball, it's a rigid object and all of the particles are moving at the same velocity. But suppose we were to take a bungee cord. They aren't all moving at the same velocity if the bungee cord is stretching. If we take a baseball and we spin the baseball and we want to talk about how fast the particles are spinning, not all the particles are spinning at the same velocity. We know the particles toward the outside of the baseball are spinning much faster than the particles near the center of the baseball. Understanding the center of mass or knowing the center of mass is important in astronomy also, because when objects orbit, they orbit around the center of the mass of the system. In our solar system, we think of the planets orbiting around the center of the sun. In reality, the sun and the planets orbit around the center of mass of the solar system. Because the sun is so much more massive than the total mass of the planets, the center of mass for our solar system lies within the sun, but it isn't exactly at the center of the sun's mass. So this is an important concept. So here we have the equation for velocity. We can find the total momentum of a system if we take the velocity at the center of the mass times the total mass of the system. Let's take an example. A system is made up of object A, which has a mass of 2 kilograms, and object B, which has a mass of 4 kilograms. Object A is moving at 3 meters per second, and object B is moving at 1 meter per second. So here we have a system that, for whatever reason, the objects are moving at different velocities. What is the velocity at the object's center of mass? We use this formula, which gives us the weighted average of their velocities, and we find out that the velocity at the center of mass is 1.67 meters per second. If we're asked what is the total momentum of the system, since momentum is mass times velocity, the momentum of the system is going to be the system mass times the velocity at the system's center of mass. And in this case, it would be 10 kilograms times meters per second. Let's move on now, and instead of looking at systems of particles, let's look at extended objects. An extended object is an object that's made up of many contiguous particles rather than particles that are separated by a distance. When we do that, we want to treat the object as if it's made of small chunks of mass, delta m. Then we can use our equations to find the center of mass along each axis by adding up all these little chunks of mass, delta m, times their coordinates along the x, y, and z axes. If we shrink the chunks so that the mass approaches zero, our weighted average formula becomes a Riemann sum, the limit of delta m as it approaches zero, the sum of all the position mass products divided by the total system mass. And of course, we can rewrite this Riemann sum in the numerator as an integral of x dm times the constant 1 over system mass. We can do the same thing for the y and z axes, and this gives us our general equations for finding the center of mass of extended objects. Let's take a look at a rod of uniform distribution. So this rod has a length L. It's a relatively thin rod, which means its diameter is much smaller than its length L. And we're going to make the x-axis go through the center of the rod. We're going to place the one end at the origin. And notice we're going to break it into small chunks, dx. If m is the total mass of the system, then dm is equal to m divided by L dx. We refer to this ratio, m divided by L, as the linear density, and it is the mass per unit length. So if we take the mass per unit length times the infinitesimal length dx, that gives us the infinitesimal mass m. Now we can go back to our basic equation for the center of mass, and notice this integral is x dm. Now that we have this expression up here for dm as a function of dx, we can make that substitution. So we have the integral from 0 to L of x times the linear density dx. And we can go ahead and solve this integral. We can evaluate it from 0 to L because that's the length of the rod. And what we wind up with is, with a uniform density, the center of mass is L divided by 2, or in other words, right in the middle. That, of course, doesn't surprise us since it's uniform mass. Because we ran the x-axis right through the middle of this rod, we know that y and z are equal to 0 by symmetry, because there's just as much of the rod on the positive side of these axes as there is on the negative side of these axes. Let's move on and look at a rod that has non-uniform distribution of mass. And we're going to let the linear density vary as a function of x. That's what it means when we say it's nonlinear. We're going to look at a specific case where the linear density is equal to a constant alpha times x. In other words, as we move away from the origin, the mass of the rod is going to get heavier and heavier per unit length. Then we can go ahead and set up our general equation for the center of mass along the x-axis. We start with our equation, 1 over system mass, the integral x dm. We need to make a substitution for dm, that is lambda dx. We go ahead and solve this integral, and we wind up with the center of mass is equal to lambda, the length cubed, divided by 3m. Notice we still have the system mass in here, and we still have this specific constant alpha. We'd like to go ahead and get rid of those, so we have some more manipulating to do. We can make a substitution for alpha. If we go ahead and look at total system mass, the total system mass is just the integral dm. We know that dm is equal to lambda dx. We can make the substitution alpha times x for the lambda, and we can evaluate this integral, and we're left with lambda L squared divided by 2. Go ahead and rearrange this algebraically to get alpha, and alpha is equal to 2m divided by L squared. We can make this substitution into our original expression up here for the center of mass. That leaves us with the center of mass is going to be at 2/3 the length of the rod when we have a non-uniform mass distribution that is proportional to the distance from the origin. Let's look at one more extended object, a triangle, and we're going to find the center of mass of this triangle. Take a look at some of the key functions here. We've got a right triangle. I've gone ahead and labeled the coordinates of the vertices. And this triangle has a mass of 3 kilograms. And we're going to be looking at small slivers of this triangle that have a width dx, a height of y, and a mass dm. So we're going to be looking at these different chunks of the triangle. We start with our general equation for the center of mass, and we need to make a substitution for dm. Now this is different than it was for a thin rod. dm is going to be equal to the total mass of the triangle times this ratio, which is the area of this small strip divided by the area of the total triangle. Here's the expression for dm for this specific triangle. We substitute this in our integral for dm, and we go ahead and simplify this, and we back out the constant of 1/8, and we have the integral of xy dx. Y equals x, since the height and base of the triangle are the same length. Notice that this ratio does not always have to be 1:1, but based on the lengths of the side, you will develop an expression for y in terms of x, and you're going to have to make this substitution for y in the equation. Notice that when x and y are equal to each other, the coefficient of x squared will be 1. If the sides are not equal to each other, then you're going to have a coefficient other than 1, and it could be less than 1 or greater than 1. We go ahead and evaluate this expression from 0 to 4, and we're left with 2.67 meters to the right of the 4,1 vertice. Now we need to look at the y coordinate, center of mass. We're going to go through a similar process. Because the sides are the same length, we're going to wind up with exactly the same number. If the sides were not the same length, then we're still going to follow the same process up here, but our integral and our final evaluation is not going to be exactly the same. In this case it is, and we have the location of the center of mass for this triangle is 6.67 meters, 3.67 meters. It's not 2.67, 2.67 because this point is not at the origin. This point is at 4,1, so we had to add the 2.67 to that starting coordinate to come up with our center of mass. Well, this wraps up our discussion on center of mass. I hope you have a new appreciation for it and why it's important in mechanics, and have a good day.